is here.
All right, are we good to go?
We're good.
All right. Hello, welcome to Clean Coders. My name is Chris Powers, and I'm very excited to kick off the first episode of this new series, Clean Code in the Browser. We're going to be spending a good amount of time with one another here, so we should get to know each other a little better. I guess I'll start. Now, I'm not going to lie to you. It was not always my first career ambition to be a technologist. I don't have a CS degree. I've never actually taken a programming class in my life. When other kids were trying to become rock star programmers, I was a lot more interested in being, well, an actual rock star. After graduating from college with a bachelor's degree in music, I toured with a band for a couple of years. We never made it, per se, but I sure learned a lot about collaboratively building and selling products. It's fascinating how many parallels you can find between music and software, and we'll talk a bit about that later. One fateful day, my band decided that we needed a website, and we were broke, so there was no way that we were going to hire somebody to make it for us. So I went out, I found a free copy of Dreamweaver, I wrote some unbelievably bad code, and I was hooked. I probably rewrote that website 10 times over as I learned new languages and new frameworks. There was a lot of flash, it was not my proudest moment. At some point, I had a realization. What if I took my career of music and my hobby of coding and I just switched them? Well, I could still be creative and create cool things, but I might get paid. 11 years later, I am really glad I made that decision. Since then, I've been in a variety of roles on software development teams. I started out as a designer and quickly became a front-end developer, learned how to be a back-end developer and a full-stack developer. I was a team lead, and then I ended up joining the management track, and now I solve a totally different set of problems. I've been at small companies and at huge companies. I've been a consultant, and I've been a startup CTO. One of the great things about having experienced all these roles in different organizations is getting to see the patterns that lead towards success or to failure. Over time, you get better at kind of picking out those behaviors that are going to lead you to a successful outcome and avoid the ones that are going to lead to failure. The good news is that I'm getting much better at finding these patterns. Of course, the bad news is the reason for that is that I have seen a lot of failed web projects. Way too many failed projects.
So why is it that projects fail? I mean, there's a lot of possible reasons, probably as many different failure modes as there are projects themselves. Every project is a delicate mix of business goals and technical considerations, team dynamics, deadlines, milestones, and any piece of that could lead to a failure. Even given all of these ways the projects can fail, there's one particular kind of failure that really has my attention. I have seen this at every company that I've worked with, every single one. These projects weren't failing because the business requirements were unclear or murky. They weren't failing due to technical limitations like a database not scaling. It wasn't lack of staffing, it wasn't leadership meddling. The deadlines were reasonable and the goals were achievable. Every one of these projects failed because the cost of maintaining the front-end code base became prohibitively expensive. The HTML, CSS, JavaScript, and app servers. These projects were doomed because of front-end code.
You've probably seen this pattern before. It is finally time to build a new application. It might be customer-facing or it might be internal, but regardless, your team is super excited about it. For developers, there is nothing as enticing as the promise of a greenfield project. This is the chance for a clean start. No more working on those terrible legacy systems. This project is going to be different. Management is also excited. This project could be a big win for the company. The developers are happy, there's energy and momentum around the project, things are looking great. And initially, things do go great. It's a little slow starting off. There's picking conventions and tool sets and making some upfront architecture decisions, but no one's really worried about this at this point. I mean, besides, we want to make sure that we get it right the first time. Once the team starts to acclimate and the project is gelling, things really take off. Features are being built rapidly. Management is thrilled, and developers are feeling alive. Every day in the office is a party. Of course, that pace never really seems to last. Once all the easy problems are solved, well, everything gets a whole lot more complicated. Developers are still working hard and delivering features at almost the same rate, but cracks are starting to show. The abstractions they started with aren't supporting the new behaviors as well as they'd hoped. The tools they picked aren't quite the silver bullets they'd imagined. Everything seems to be getting harder, but the developers assume that's just what happens as a codebase gets bigger. At this point, no one is consciously deciding to sacrifice code quality, but it's taking all the team's effort to maintain their current velocity. Management, on the other hand, is blissfully unaware that trouble is brewing in the codebase. The team is still making progress, and the burn down charts are still going down and to the right, so the project barrels forward. At this point, things are starting to look bad. Our velocity keeps going down. We're padding estimates more heavily, our iterations are getting smaller, and yet still, goals aren't being met. Developers start murmuring about doing code debt iterations and refactoring projects. Of course, anytime that a developer does go off for a few weeks to do a refactoring project, somehow they always come back with more bugs and regressions, and it takes even longer to fix that. The team is in crisis. When they try to push through the mire and release new features, the situation gets worse. When they push off new features and try to improve the codebase, it doesn't get much better. Return on investment of making any changes at all is suddenly very unclear. Despair sets in. Developers are clearly cutting corners to provide some semblance of velocity, but the bug rate is high enough now that it hardly matters. Inevitably, developers start leaving the team. That's it! I quit! I quit! I'm done! I'm out! New developers are brought onto the team. Without knowing how the codebase came to be, immediately they assume that the original authors were complete idiots. The Greenfield project is suddenly being referred to as the legacy system, and the new developers are scared to even touch it. At this point, it's only a matter of time until someone utters the most dangerous word in all of software development: rewrite. At first, this decision does not go over well with management. Rewrite? Rewrite? You have got to be kidding me. But after thinking about it, he doesn't really have a choice. The project is dead in the water. I mean, there is no clear path from where they are now to where they need to be in order to get that big business win. But a rewrite, well, that gives everybody hope. I mean, with a new Greenfield project, we could start fresh, get it right, avoid all the problems that caused us to fail the first time. Now that sounds pretty good. Now wait a second. This sounds strangely familiar. Well, of course it does. It's the same flawed logic that we used when we started this project in the first place. And yet, without any other better options, the inevitable rewrite project begins. And history repeats itself. Again. So why are we talking about failed projects like this? Well, remember, these failed projects were not due to misguided management or poor planning. The team thought that the deadlines were reasonable and that the goals were achievable. Ultimately, the crumbling of both the product and the team were directly attributed to the poor quality of the code base. Degradation of code is something that happens across all technologies and stacks. And yet, there is something about front-end web projects that seems to attract poor quality. We're going to talk about 3 factors that leave front-end web projects particularly prone to unclean code. The first one is history. The history of the web has been riddled with poor quality code. An entire generation of developers came into it with low expectations for how front-end code could be constructed.
Secondly, there's the problem of divided developers. Over the last 15 years, we've seen a strong polarization as developers have specialized as front-end or back-end. Unfortunately, this division has caused the groups not to learn from one another and share best practices. Finally, the inherent client-server architecture of front-end web applications introduces some unique challenges to code quality. Maintaining best practices like SRP, dry, and separation of concerns can be surprisingly challenging and is often overlooked. This series is dedicated to applying the principles of clean code to the browser environment. By first taking a look at the historical and cultural forces that are setting our developers up for failure, we can start to take meaningful steps towards reversing those forces. So let's start by taking a look at the history of code quality on the web. Let's go back to the 90s and talk about the foundation of the web, HTML. The vision that Tim Berners-Lee originally had for the web was elegantly simple. Create a decentralized web of HTML pages joined together by links. He correctly identified that for this to be successful, the cost of adoption of the technology would need to be very small. In his alt hypertext message entitled World Wide Web Summary, he states that the very small startup effort is designed to allow small contributions. Small contributions of 1 or 2 web pages were not being ignored. In fact, they were seen as critical to the success of the web. Now, this put the impetus on the web browsers. They were going to have to do all the heavy lifting. The rendering of the pages was up to them, while the authors only had to worry about creating and hosting the content. This architecture was clearly successful at gaining adoption, but it came at an interesting price. Now there was a disconnect between the execution environment of the browser and the application context. Developers couldn't control what browser implementations were being used to view their websites, and so things that they had traditionally taken for granted now were called into question. For example, what happens when something goes wrong? How should basic errors like parsing errors or syntax errors in the HTML be handled? In a traditional application environment, you would have choices. You could certainly just let the error bubble up and crash the program. You could catch it and prevent a user from knowing there ever was an error. You could have retries, you could log the errors, you could have fallbacks. When your software is being executed in a remote, walled-off environment like the browser, it's not immediately obvious what the right way is to do error handling. Now, HTML is just a declarative markup language. It has no mechanisms for dealing with errors, and so it's up to the browser specifications. You can imagine that decision going one of 2 ways. Either the browsers could decide to just bubble up those errors and display an error page to users. The other possibility is the browser could do everything in its power to not display an error page to a user. Now, as we all know, browsers try really hard not to fail. Come hell or high water, they are going to display something to that user. And it makes sense. I mean, remember, the web has always been optimized for ease of adoption. A lenient policy towards error handling was going to be much more attractive than the daunting prospect of displaying error pages to users. What if one Internet Explorer quirk could cause your website to be unavailable for all those users? Or on an e-commerce site, what if a missing closing tag caused the checkout page to never render? This really would have scared off early publishers and users. Publishers want to make sure that their content is always available, and users don't care about technical errors, they just want to be able to see that content. So how is it that browsers can render invalid markup? Well, the truth is, I have no idea. Let's take a look at this behavior in a couple browsers and see how they compare.
So I'm going to warn you, there is a lot of voodoo stuff going on in here. It's not immediately obvious what the best way is to take invalid markup and just magically turn it into valid markup. And because of that, every browser, at least historically, has done it a different way. Let's take a look and see how Chrome renders invalid markup differently than Internet Explorer.
Alright, let's start with a trivial bit of HTML. This code is syntactically correct, and it's valid markup. When we go over to Chrome to take a look at how it renders, well, there's no surprises here. This is what I expected to see. Let's go back to the code, and now we're going to make a few changes to make this HTML invalid. The first thing I'm going to do is get rid of these quotation marks around the class name. An HTML attribute is only going to be valid if it is surrounded by quotation marks. Secondly, I'm going to delete that opening strong tag, but I'm going to leave the closing strong tag in just to see what happens. Finally, let's take this header and nest it inside of the paragraph tag. It is invalid to nest header elements inside paragraphs, so this should cause some problems for us as well.
Now remember, in any other language, if we intentionally put syntax errors into our code, the program would break. Whether it was Java, or Ruby, or Python, or even JavaScript, it's going to either fail to compile, or it's going to throw errors. And yet this is HTML. Let's see what the browser does.
Surprisingly, not much has changed. We see that my name is no longer bold. Of course, that makes sense because we had removed that opening strong tag. Let's take a look at the DOM inspector so we can see how Chrome dealt with our invalid markup. So as we open up the body tag here, the first thing that we see is that the byline class, which we had removed the quotation marks from, once again has quotation marks. Apparently Chrome was able to add that automatically. Also, we used to have that closing strong tag here. Now that's gone. When Chrome saw that there was no opening tag to match, it just pulled that closing tag out. Now the next piece is a little more complicated. So when we had the header inside of the paragraph tag, it looks like what Chrome did is it first started a paragraph tag but then closed it early. It then had the header tag, which is no longer inside of the paragraph tag, making it valid. Strangely, the original contents of the paragraph tag just ended up hanging out here as a text node, and then I guess just for fun, we threw in an empty paragraph node to just wrap it all up. Now this is kind of strange behavior. This is not exactly what we originally intended, but I will point out that if we hadn't looked at the code and we had only looked at the rendering up here, we probably wouldn't have noticed a difference.
This behavior is truly remarkable. We put 3 blatant errors into our HTML, and the browser just fixed it. We didn't see an error as a user, and in fact, when we opened up the developer console, we didn't see any errors there either. The reason for that is that the problem was solved by the HTML parser. By the time that markup actually got to the DOM and was rendered, it was valid. There were no problems with that. Sometimes we don't get so lucky. Let's try adding another error that will actually have a negative effect on our user experience.
Okay, so this time, let's say that I fat finger a closing tag and I accidentally omit that backslash. Now this header tag is invalid because it's not properly closed. What is the browser going to do with this? Let's take a look in Chrome again. Okay, so we can see now that this line, which was not originally a header, now looks like a header. That is not quite the same. Looking in the DOM inspector, we can see that we now have 2 fully closed H1 tags. So the good news is that Chrome is smart enough to know that you can't put a header inside of another header. So it closed off this H1 right before it reached the second H1 tag. And then it's smart enough to have put a closing H1 tag right before the H2 tag. Now obviously this page looks wrong. It does not represent the original intent of the author. It is, however, still legible. A reader could come to this page and get the information they needed, even if there were errors. But wait a minute. What if we open this invalid document in another browser? Will we see the same behaviors? Let's switch over to the bane of web developers' existence, Internet Explorer. Whoa. Internet Explorer is clearly showing us a different rendering than Chrome. Let's use the DOM inspector to look at the differences. The big difference that I see is that IE handled these H1 tags differently.
Rather than closing the first H1 before the next H1 began, it nested all of the content inside the first header. This results in HTML that is still invalid. The HTML spec says that headers cannot be nested inside of other headers. Still, IE has placed an H1 inside another H1, and the H2 down here is nested even further inside of them. So this explains why the view looks so bizarre. In Chrome, synopsis was an H2 header, and this paragraph tag looked like a paragraph tag. But now here, the paragraph tag looks like an H1. It has those styles that it inherited from this nesting. And strangely enough, the H2 apparently kept its styles even though it was nested inside of an H1. In cases of invalid HTML, it's kind of hard to decide what the correct behavior is in these situations. And here lies the big problem of having all of the important logic for rendering HTML pages live inside of each of these browsers. Inconsistencies between vendors and between browsers causes big headaches for front-end developers.
Tim Berners-Lee's vision for the World Wide Web came to fruition. HTML pages were easy to create and, frankly, were hard to screw up. Whether you were creating giant e-commerce solutions or just GeoCities pages about disc golf, you were contributing to the success of the World Wide Web. Unfortunately, you were probably contributing to one of the web's biggest problems as well. When we look at human interactions and behaviors, we see that permitted behaviors are oftentimes interpreted as being beneficial behaviors when they closely align to our own personal motivations. A few years back, there was a study that showed that butter was not actually as terrible for us as we thought. Within reason, the study was giving us permission to use butter as part of a healthy lifestyle. When this study was first released, I knew a few people who took this permission to be a prescription. They thought that butter was some kind of a superfood, and they started using it in everything. Obviously, this is not actually what the study said. There was a false equivalence being made between permission and prescription. These people just loved butter. They wanted to take any kind of pro-butter idea that they found and work it into their own existing cognitive bias. They think the butter is good, a study says it's not bad, therefore it must be good. The same thing happened to HTML as the web exploded in size. As we saw earlier, browsers are very permissive. Authors are able to publish invalid markup with very few negative repercussions. For better or for worse, web developers tend to be incentivized to just get something done out the door and move on. This permission to write invalid HTML oftentimes became a prescription for anyone who is okay with creating good enough HTML and moving on to the next thing. In the late 90s, it was estimated that 99% of all web pages had at least one error. 99%! That is nothing short of an epidemic. That means that 99% of web developers either didn't know how to write valid markup or didn't think it was important. An entire community of developers had created a culture where clean code was not important. So what was the cost of this culture? Well, remember back in the day when websites used to put some kind of a banner that would say, best viewed in Firefox or best seen in Internet Explorer? That was one of the many repercussions of writing invalid code that is hard to understand and it's hard to maintain. Cross-browser compatibility is incredibly hard as is. Now you throw in the extra problem of having browser-specific behaviors on auto-correction of invalid markup, and it's a nightmare. So, developers gave up. They told users, just use a single browser, and they called it a day. There were attempts to solve this problem. Do you remember Xhtml? It got a lot of attention between 2000 and 2010. During that time, XML was becoming very popular. A lot of people wished that HTML worked similarly. So Xhtml was taking the rigor of XML and applying it to HTML. For example, in HTML, it's perfectly acceptable to never close a paragraph tag. There are some tags, like line breaks and horizontal rules, that were never intended to be closed at all. XML and XHTML are much more demanding. They require that all tags be closed. Even tags that have no body content still have to be self-closing. Now, if you're looking through some HTML code today and you see some of these self-closing tags, it's a good chance that the person who wrote that used to write XHTML. I still do it all the time. It's a hard habit to break. The most controversial feature of XHTML may have also been its most useful feature. It was referred to as Draconian error handling. Now, Draconian refers to Draco, an ancient Greek legislator who was well known for having ridiculously harsh punishments for relatively small crimes. For example, according to Draco, stealing a cabbage was worthy of the death penalty.
No, wait. I paid for this cabbage.
Okay, enough about Draco. The point is that Draconian error handling was meant to be the opposite of the existing silent and lenient HTML error handling. Under XHTML, if there was any kind of markup error, an error screen would be displayed to the user. This is an attempt to completely reverse the pattern of the last 10 to 20 years. A system that was originally defined by leniency would now become a zero-tolerance system. If XHTML had taken hold, I could imagine some benefits. The culture of poor code quality on the web would immediately be reversed. That 99% error rate would plummet to 0. Tooling would quickly develop server-side to ensure that only valid HTML pages were ever delivered to users. HTML code quality libraries would be a given part of Web Toolkits. But as you know, we're not using XHTML. XHTML lost out to the HTML5 spec, and it was largely the Draconian error handling that killed it. There was no clear migration plan that took you from the lenient HTML rules to the strict XHTML rules. And frankly, the risk of possibly showing these error pages to your users was very high. Let's say that you had built an e-commerce site, yet somehow an HTML markup error had worked its way into your checkout page. Now, when anyone wants to buy something, they see an error page. This would be disastrous. And ultimately, the web development community said they couldn't stomach that kind of risk, especially if the only benefit of it was going to be having valid HTML markup across the web.
So here we are. We're building software and environments that place quality solely in the hands of developers. And we're inheriting from a culture that has sacrificed quality for speed. So far, we've only talked about HTML. It's the oldest of the web technologies. Unfortunately, the history of CSS and JavaScript is not really any better. They've also been plagued by lax attitudes towards quality. So how do we turn the tides? How do we embrace clean code? The truth is, the clean coding principles aren't really new or novel ideas in web development. Right now, there's organizations building software where the front-end developers are struggling to use clean code, but the back-end developers are using the same quality practices that they've been using for years.
Too often these people just aren't talking to each other. They're not sharing these ideas.
So why is this? Well, it comes down to the common problem of having divided developers.
Drums and bass. The foundation of popular music for the last 100 years. The yin and the yang of modern music. It's the chocolate and vanilla, it's the peanut butter and jelly, the sushi and Doritos. I think what Shakespeare here is trying to explain is that music really does need both the drums and the bass. It's not quite right if you're missing one or the other, which is really unfortunate seeing as most drummers are complete morons. Whoa, whoa, whoa. That's pretty big talk for somebody who can only play E, A, and B. Good luck playing in another key, if you know what a key is. Yes, I know what a key is. That's what the capo is for. Look, on their own, neither the drums nor the bass has a lot going for it. I mean, have you heard a bass solo before? Oh. Oh, it's like a Schoenberg piece gone so wrong. And you think you can do better? All right. Oh, give it a rest. It sounds like you just took your drums and threw them down a stairwell. Needless to say, drummers and bassists don't always see eye to eye. And yet, when you take the two pieces and put them together, music happens. I mean, there's an entire genre just called drum and bass. When you take a throbbing bass line and a steady drum groove and you put them together, it's hard to go wrong. Being both a developer and a musician, I can safely say that both of these groups can have pretty big egos. That's unsurprising why. For a musician, it's extremely difficult to be successful in a very crowded industry. For software developers, it's very difficult to master that craft. When you get big personalities with differing opinions in the room, it can be very difficult to create that collaboration that's needed to ship successful projects. And this is a real problem. While we may have developers who aspire to one day be the next Linus or DHH, at the end of the day, programming is a team sport. We call it software engineering for a reason, because it's engineering. Good engineering requires robust support, risk mitigation, and a deep understanding of the domain and the system. Mature organizations just can't risk their systems with cowboy coders or lone wolves. There's way too much at stake. On web development teams, we often see this division between front-end developers and back-end developers. Much like with bassists and drummers, there can be very large differences between these groups, different backgrounds and interests and best practices. And yet the software projects that we create can't be successful until both of these groups are able to collaborate and ship. Let's go take a walk.
I've been building software for the last 11 years now, and one of the things that I've felt over that whole time is kind of this fundamental disconnect between the developers who are working on the front end and on the back end. Seems like it's always been there. And so I asked some of the guys who, have been doing this a lot longer than I have, I said, is this something that's always existed? Has there always been this rift, or is it something new? Is this a thing that belongs to the web, or was that something that was in place before? The consensus was that the role of UI developer or front-end developer didn't really exist prior to the early 2000s, and it was specifically for the web. Back in the 80s and the 90s, no one was really talking about user experience design. It was the programmers who were building the GUIs, although certainly marketing would jump in with their ideas as well. Now, platforms would actually publish style guides that designers and developers could use to make decisions about what their UI should look like. The early web had a similar story. HTML 1 and 2 and 3, they had very few capabilities for actually building a compelling user experience. Now the real programming work was all on the back end. It was figuring out how could we make this scale given the explosion that the web was experiencing. Building some of those first online platforms was an unprecedented challenge with very little pre-existing architecture to build upon. The front end, on the other hand, well, it's pretty much text output with some HTML tags thrown in it. It was no big deal. In the late 90s, we saw some slightly more interesting things happening in the browser. Developers figured out how to take tables and nest them inside of other tables and nest them inside of other tables and get complicated layouts that they couldn't have before. There was also tooling like Dreamweaver, God help us, which would allow developers to slice up Photoshop documents and automatically generate HTML that would load in the browser and glue it all back together again. Browser capabilities continued to improve. HTML4 added a lot of new features, and CSS was finally getting implemented for real. Now, JavaScript, it was still a tire fire, to be honest, but the tooling was getting better, and developers were starting to take it seriously. Now, don't get me wrong, I mean, Internet Explorer 6, it was terrible. But if you compared it to Internet Explorer 5, it was one heck of an improvement. Do you remember the first time that you used Gmail or Google Maps? If you'd worked in the industry back in 2004, I'm sure that you do remember that. I mean, now it just seems normal, right? We take it for granted. But 12 years ago, no one had seen anything like those applications before. I mean, where were the page reloads? Where was that sluggish performance that we all knew divided the web apps from the native apps? The Web 2.0 boom had been born. These groundbreaking projects changed the way the product teams looked at their platform and the capabilities. And it changed the way that users looked at the web and thought about what it could and should do. There was really only one problem, and that's that building apps like these was incredibly difficult. The specifications for HTML and CSS and JavaScript were always changing. The number of quirks across the browsers and cross-browser compatibility issues was overwhelming. So with all of these new capabilities and all of this new work, the next question became, well, who's going to do all that work? Now, the first logical thought is, let's take the programmers who were currently building out the UI and have them do it. But this was problematic. See, given all of these new capabilities, the amount of time that was going to need to be invested in learning them and in building these new UIs was significant. We were no longer just spitting out HTML encoded strings. No, now we were actually having applications that were building applications. Now, many developers decided that they wanted to stick with the server-side technologies. It's what they were best at, it's what they've been doing all this time. They provide a lot of value doing it. Other developers decided that they would take the plunge. They wanted to try this front-end thing out. And so they wanted to master both the front end and the back end. They became the legendary full-stack developers. Yet, that wasn't enough. The demand for rich client applications was exploding. We needed more people, and we needed them now. And that's where I came in. So to meet this demand, a new cohort of programmers entered the industry, myself included. Our backgrounds were a little different. Generally, we started out as designers or hobbyists. Didn't have CS degrees, didn't have formal programming training. We knew enough HTML and CSS to slap together some web pages, maybe could fake a little bit of JavaScript. We were happy to pick up some of those CS fundamentals along the way that we had missed, but until then, we barreled forward. The mid-2000s provided fertile ground for these new developers who were taking on these front-end positions, especially those who had come from other careers. 5 years earlier, there was no way this boom could have happened. There wasn't enough demand for UI work, and the tooling and the instructions that were available were terrible. The learning curve was just way too steep. In a similar way, it would be very difficult to have that boom happen today, in 2016. The number of dependencies that are required in order to be effective in the front-end space today, it's insane. I mean, you've got all of the HTML5, you've got Flexbox, you've got JavaScript compilers and minifiers, you've got higher level languages, I could go on and on, there's so many of them. The learning curve is incredibly steep, much more than 10 years ago. Now in 2006, the doors of opportunity flung wide open for front-end developers. The demand for that specialization was very large. HTML4 and CSS were challenging, but certainly manageable, and developers were able to quickly put together web pages. Ruby on Rails was released, and it was a very easy program for someone to use to get up to speed on both the front end and back end side of the web. Jquery was released, and that solved a lot of the problems that developers had been having with JavaScript and the DOM. It also took care of some cross-browser compatibilities that had plagued developers for years. Tooling like Firebug had just come out and was proving to be very valuable for front-end developers. They had a new level of insight into their markup and their styles and their behaviors that they had never had before. Along with that, blogs were suddenly becoming very popular in tech circles. Now people were learning and sharing these learnings with the rest of the community. Along those lines, it was only a couple of years later that Stack Overflow went live. Suddenly, all the answers to your questions were just one Google away. So what happened when you took the traditional programmers and dropped in a whole bunch of new front-end developers? Well, a lot of good things happened. Suddenly we were able to take projects that were stuck and they started moving forward. They were fueled by having the right people with the right skills, and they were excited about the roles that they had on the team. Backend developers were elated that finally there was someone else to do that UI stuff and they could focus on the problems that they wanted to solve. Front-end developers were thrilled to be working on the code that users were actually interacting with. And they were pretty thankful that there were back-end developers to do that heavy lifting. Unfortunately, there were also problems. Some divisions were starting to form between these two groups. Now, it was easy to make fun of HTML, CSS, and JavaScript and say they weren't real programming languages. I mean, it's shooting fish in the barrel. The problem was that also started to make people think that these front-end developers weren't real programmers. Now, to add to that, some front-end developers were stoking the fire as well, suggesting that the real application was the UI code. After all, that was what the users, the ones who were paying the bills, were actually seeing. Perhaps all those services were really just there to support the work that the front-end developers were doing. It was us versus them, and unfortunately there was very little understanding and empathy between the two groups. The idea that front-end code somehow wasn't real code, it was pervasive and it was dangerous. If front-end code wasn't real code, then front-end developers might not be real developers. And if that was the case, then they weren't being held to the same standards of quality that real programmers were held to. Sure enough, automated testing, totally missing, and regressions were all over the place. Performance testing wasn't a thing, and design and architecture, no one was talking about it. The patterns and processes that gave us quality and reliability on the back end were suspiciously missing from the front end, and this went on for years. Really, what the front-end developers were being graded on wasn't their code quality, it was usually how closely did their end product match those Photoshop mocks that the designers had put together. Since poor code quality was something that the team had deemed as permissible, they took it as a prescription to slap together unprofessional software. So what can we learn from all of this? We know where we've been, but how do we move forward? Well, the first thing that we need to do is to recognize that the us versus them mentality is killing our teams and it's killing our products. There is no them, it is only us. Our products cannot be built with half the team. We need all parts of the system engaged in order to ship working software. So what good is a back-end system that has no front end to expose that functionality to users? Well, it has no value. I mean, remember, from a user perspective, the UI is the application. On the flip side, what good is a UI that has no back-end services to draw upon? At best, it's just going to be a brochure site if it can't actually do anything for the user. No, we need to acknowledge that our successes are deeply dependent on the performance and the quality of all of our team members. We have a professional responsibility to both invest in our team members as well as demand high-quality work from them. You are your brother's keeper, whether you like it or not. It's up to every team to decide the level of quality and rigor that they expect, but those expectations should be consistent across both the front end and the back end. Beyond just the sake of your project, closing the gap between developers can be really good for your career. Companies are always looking for full stack developers, people who have skills both on the front end and on the back end, but they're really hard to find. They usually get called unicorns. By learning both of these skills from your peers, you can make yourself much more valuable in your current position as well as in your next job search. Front-end developers, especially ones with backgrounds like mine, can learn a lot from our back-end counterparts about CS fundamentals. And back-end developers have a lot to learn as well: product development cycles and iterative experimentation. Diverse teams consistently beat out homogeneous teams because they get the best ideas on the table and they're constantly sharing and learning from each other. Unfortunately, that's just not how it works. You can't just push your knowledge on someone and hope that they receive it. It's a recipe for disaster. The learner needs to be the one to take that first step to cross that gap, to expose their ignorance and ask for help to get better. Now that takes some trust, but once that trust is built, the second time becomes much easier. And the team gets to see that exposing your ignorance, it doesn't show weakness, it's actually a tool for learning. So it's up to you to take that first step, to bridge the gap and expose your ignorance. Show your team how effective it can be. Divided developers has kept us from high quality for far too long. Now is the time to fix it.
So far we've talked about the cultural and relational forces that set the stage for poor code quality in our front-end code bases. Now I want to talk about a big challenge technically, the client-server architecture. The client-server architecture has been around for a very long time, longer than the internet in fact. One of the first appearances of the architecture was actually in a project called Arpanet back in the 1960s. Arpanet was one of the first networks to implement the TCP/IP protocol. It was an early experiment in packet switching. The network was being developed by the Advanced Research Projects Agency, or ARPA, and the Department of Defense in order to create a network that was going to be more reliable and robust for military intelligence. At that point in time, computers were becoming a little more prevalent, but they were still incredibly expensive. The advantage of the client-server model was that it allowed an organization to cluster its computing resources and make them available to a large number of people. It was a fat server, dumb client architecture. Let's see. Let's say that this giant bantha represents our fat server. Now the server is where we would invest the majority of our resources. All business logic and capabilities would be centralized on this expensive hardware, and that would make the functionality available to less expensive client devices. Let's say that these stormtroopers represent the client devices. Now these devices are as dumb as possible, and they miss everything they shoot at. Imagine a mainframe with terminals. The mainframe has all of the business knowledge, and the terminals are completely dumb. Whatever the user enters into the terminal gets sent up to the mainframe, and whatever gets sent from the mainframe to the terminals is pretty much just blindly displayed to the user. The terminal can't really do anything for itself. It's completely beholden to the server. This architecture was dominant for years, really until personal computers became a reality. At that point, the end user's machines were powerful enough that they could be much smarter. We no longer needed to centralize all the resources into the server. In fact, it became much more efficient to spread that work out and to build applications that actually ran in the client devices. So in the 80s and 90s, we saw a migration away from client server and towards installable apps that ran on PCs. While businesses were able to use their networks in order to connect their workstations, a whole new set of PC users didn't have network access, and this made a serverless architecture very attractive for mass adoption. Now fast forward 15 years, and the internet has completely turned this on its head. Thanks to the World Wide Web and a lot of AOL CDs with 1,000 free hours on them, a whole horde of new users had browsers that could talk to servers. While the user's PC was a perfectly capable device, the browser that was loaded inside of it was not. The early browsers were practically a throwback to the dumb terminals. They displayed the content received from the server, and they could send simple get and post requests through links and forms. And that was it. Browsers couldn't even store state. Given the simplicity, it was up to the fat server to do all the hard work. It had the data, the business logic, the session state, and all the functionality, and it had to scale out to serve a growing population of internet users. The client-server relationship was well defined. Fat server, dumb clients. This relationship lasted until the mid-2000s. Over that time, the browser capabilities had improved. They now supported HTML4, more CSS, more JavaScript. Pages were able to render with much more complexity, but it didn't really change the role that the browser had in the system. Cross-browser compatibility concerns were still huge, and developers were best off keeping it simple and focusing on server code. Everything changed when AJAX techniques were introduced. As a reminder, AJAX is an anagram that stands for Asynchronous JavaScript and XML. It's actually a pretty terrible name. I mean, technically AJAX can be synchronous, and JavaScript is inferred. XML is rarely used for it anymore. And you use AND as part of the acronym? Really? Well, regardless of names, AJAX was a big deal. It allowed the browser to fetch resources and data from the server without refreshing the page. This opened the doors for a new set of web apps that felt more like desktop apps, kind of like Gmail and Google Maps, which were revolutionary. Browsers had now grown to the point where they no longer had to be dumb clients, and instead could have a large amount of control. The business logic for data manipulation, view rendering, and interaction handlers could now reside directly in the browser. These new browser capabilities provided for some new user interactions, but what was the impact on code quality? Well, up until this point, most web developers hadn't really done much JavaScript. If anything, they probably just jammed some into on-click handlers on links. When the fat server is doing all of the hard work, JavaScript's just a nice to have. Suddenly, JavaScript was in charge of managing data, rendering views, dealing with user input. Now, JavaScript lacked a lot of the key pieces of a language that you would expect to be there. There was no module system, there were no proper classes. It wasn't clear how you would build and maintain a very large application. What JavaScript developers did have, though, was jQuery. And thank goodness. jQuery took away a lot of the problems that developers had with raw JavaScript. Complicated things like user interactions, DOM manipulation, view rendering, even state management. jQuery could do it all. Unfortunately, this Swiss Army knife unintentionally encouraged a lot of jQuery spaghetti code. There was no separation of concerns, and if there were any modules in the code, they didn't live up to single responsibility principle. Let's take a look at some example jQuery spaghetti code.
So here we have about 10 lines of what I would call jQuery spaghetti. Now, 5 years ago or so, if you had asked me what I thought of this code, to be honest, I'd probably say it looks fine. It looks like most jQuery code that I was seeing at the time. There's a lot going on. There's a lot of different ideas happening, but it's clear enough if you read line by line what's going on. But what I wouldn't have acknowledged at the time is the fact that there are a lot of different ideas that don't belong together. Yet because the jQuery library allows you to access all those ideas in one place, well, it's kind of natural to try to do so if you're not being careful to keep a separation of concerns. So let's take a look at this and figure out what is this doing and what are all of the different kinds of concerns that we would like to be able to tease apart through a refactoring. So first of all, because there's DOM manipulation, we should say that this code is assuming that there's HTML on the page, that we've got an input with class name, a button with class done, and some kind of an H1 that has an ID of welcome. So first off, line 6 here, if you're familiar with jQuery, you know that this essentially means that the body of the function should not be run until DOM ready fires in the browser. So this is some kind of DOM ready, it's kind of control flow or loading logic. Next, we have a Clickhandler. This is specifically saying, what should we do if the user clicks on a button with class equal done? When that happens, we run the contents of this function. The first thing that we do is we look for an input that has a class of name, and we grab the value out of it. So this is user input. How do we fetch the user's name that they entered in? So the next thing that we do is we take the name, we split it on spaces in order to break it into a number of name parts. And then it looks like we take those parts, we take a look at the first one and see if it's Mr. or Mrs. or Dr. And if it's any of those prefixes, then we're going to shift that off so that the first index of name is going to be the first name. And that's important because in this line, here we go, we're actually using name index 0, which at that point we can assume is the first name. So it's not really that clear, but what's really happening here is we're trying to parse out the first name from a full name. Once we have that first name, then down here we do a couple things. The first thing that we do is we compose a welcome message. It'll be welcome first name. And once that's composed, then we're going to display it to user. Apparently through the element that has ID of welcome, changing that text. So this pretty much spells out all the different ideas, and we have many. We have this DOM ready control, we have click handlers that are user interactions, we have user input of actually getting text input from the user. Down below here we are displaying text to the user, we have an output, we have kind of view level message composition, and then we also kind of have more logic about how to properly take a name and to fetch the first name out of that. I should mention this is not a particularly proper algorithm, but it works for this particular example. All right, so we've so far the only changes that we have made are adding comments. Before we do any other changes, we first need to lock this down with a test. because if we want to do refactoring, we must have test coverage. Without test coverage, all we're doing is changing stuff. So I've already gone ahead and written up a test using Jasmine here. We're describing pressing the done button. We want to ensure that it displays a welcome with the first name from the input. So we do two things. The first thing is we come in and we set up a name field, set up a done button, and set up a welcome in our DOM so that our code will actually work. And then we take the actions. We're going to fill in the name field with Dr. John Doe. We're going to click the done button. And then finally, we are going to expect that when we take a look at the text of the welcome, it should be Welcome John. Come over to the terminal. I'm going to be using the Testim tool, which actually will fire up a Phantom.js, load in JavaScripts, run it all in the DOM, and then tell me whether or not my expectations are met. All right, we expected that that would pass, and it did. Let's just change this around a little bit. Just to make sure that it's failing when we think it should fail. Okay, we expected welcome John to equal welcome Dr. John, so that did fail in the way that we thought, so that's good. Let's just get back to passing. All right, so now we know that we've got some tests, and it allows us to do some refactoring. So I want to start off using a technique I like to call comment-driven refactoring. The idea is that you go through the code, labeling all of the ideas in the code with these comments. Now, the reason that you put the comments in there is because the code was probably not doing a good job of effectively informing the reader of what the intent of the author was. And this is one of the key parts to simple design in a code base, is that it needs to express the intent of the author. So by inserting these comments that tell us where the ideas are, it gives us a really good clue in terms of what ideas need to be extracted out into their own functions that would have names that make it clear what they do. Once you get to the point where you've injected enough naming into the code that now the comments seem duplicative, we can erase them. And we know that we've done an effective job of making sure that the code now reads very well because it is explaining the intent of the author. So let's start at the top. We have the DOM-ready control flow stuff here. So let's swap out this anonymous function for a named function called onDOM-ready. And we will just make this onDOM-ready. And we just need to delete a little bit of that. Let's go over to our specs and see if we're still green. Still green. All right, next, this Clickhandler. So we have a Clickhandler on button with a class of done. So let's, again, swap out this anonymous function with a named function. So on done button clicked. So we'll do that. And in fact, we'll move this all out here. Okay, so now we've got a click handler that is named. Let's see if we're still passing. Still passing, great. All right, so this click handler is pretty much obvious. We can delete that now. Let's continue on. So here we've got the user input. How do we fetch the user name? So let's use a new function called get username. And we'll just have to return that value. All right. Now the parsing out the first name from the full name. So let's say we'll do a new variable here. So first name equals parse first name from the name, let's say. Parse first name out of a full name. Let's just call it name here. So we split on the name, do the shenanigans, and then we're going to return name index 0. Let's see here. This is not going to make sense anymore. We need to change this to first name. Let's see here. We changed a lot. Let's see if this is still passing or not. Hey, it did pass. Great. All right, so now we've got some better naming here. And compose a welcome message with the first name, display welcome to the user. So let's start with composing welcome message. So let's change the contents of this to welcome message. And this is going to take the first name as an input. Check this. Still passing, great. And then, so we've composed the welcome message, but we still have displaying the welcome to a user. So this logic of this element and using the text method, this is something that can get wrapped up into a function. So let's say display welcome. This would be some kind of message. So the message would be passed in here. All right, still passing, great. So we have display welcome and welcome message. That all works pretty well. So we can delete this. So now we've gone through and we've managed to delete out all of those comments because they're no longer needed. The naming of the functions is doing a good enough job of communicating the intent that we no longer need the extra verbiage. So now we can see that we have effectively split apart and teased apart these different ideas of the code so that they can be treated separately. We have our DOM loading, we have our user interactions where we are reacting to a button click, we have user input, we have logic for parsing that first name out, logic for composing a welcome message, logic for displaying welcome messages that we have. Each of these is now separate. Now, were this a much larger system, we would probably have these in different modules, different files, different sections of the system. This is obviously a very scaled down example, but it does show that you can do this. It's just that jQuery doesn't necessarily make it easier to do this. And so it takes a little bit of a discipline and acknowledgement that we get a more flexible, maintainable system by taking these steps and maintaining the separation of concerns. Now, one last thing I want to do before leaving this code is clean up this parse first name function because it is not pretty. We've got some bad things like we're overwriting the name variable that was being passed in. That is not a great thing to do at all. So let's change this to be name parts, I think is how we're referring to it. Name parts. And we need that here too. All right, now the shifting I really don't like as well. It's kind of weird because really all we want is to get the first name, so why are we shifting things around? Let's edit this to say that we're going to return, so if name parts 0 is one of these prefixes, then I just want to return name parts 1 and just be done with it. Else, we can return this. Let's make sure that we are still passing. Great. This is not so great. Let's see here. So we could do first part equals name parts 0, so we can remove some of this duplication. Now, of course, this algorithm is very far from perfect. There's all kinds of problems with this line that I don't really want to spend time now getting into. But we've at least gotten this to a fairly reasonable place. We can read this code now. And are we still passing? Yes, we are.
JavaScript and Jquery certainly didn't make it easy to follow single responsibility principle and separation of concerns. But with a little bit of thought, a little bit of refactoring, we were able to make it work. Nowadays, there are plenty of JavaScript libraries and frameworks that will help you clarify and organize your code. But this doesn't get at the bigger problem with client-server architecture. Sure, your JavaScript could be perfect, pristine, follow all of the principles. But if you are still implementing the same features both in your client and in the server, your system is never going to be dry. Dry stands for don't repeat yourself. Now, naively, some developers think that means I don't want to ever have duplicated syntax inside of my code. Sometimes that's true, it's probably a good idea, but that's not the intent of dry. The intent is to ensure that each piece of knowledge in your system exists in exactly one place. Now that browsers could do many of the functions that the server was doing, it didn't necessarily mean that the servers could just stop doing that. For example, teams usually needed to still be able to serve up SEO-friendly pages for Google and other search crawlers. Many teams were iteratively building upon a pre-existing application rather than rebuilding it wholesale. In that case, it would be very difficult to just rip out the server components. So what tends to be duplicated? Well, first you've got URL routing. Both the client and server need to know how to handle a request URL and display the correct information. That means both sides need access to the data. What data do they need, and how do they get it? Having the raw data isn't enough, though. You have to know how to use it. Implementing data models in each environment is necessary for creating the right data abstractions. Once you have the URLs and the data, each side needs to know how to render the necessary views, what data is required, and what resources are needed to correctly render a view. Finally, view templates need to be shared so that each side can render the appropriate markup to display to the user. Now, you may have noticed that when you take all of these duplicated pieces and put them together, it pretty much adds up to the entire application. A system can never have single points of truth if every feature is being duplicated across the server and the browser. The maintenance cost of this duplication is enormous. So when your team has essentially built two applications, one in the server and one in the browser, that have to stay in sync, and both have to change anytime that there's a new feature, your code bases start looking, well, kind of like this, all chopped up and slimy. That doesn't taste very good either. Now, the good news is that we are not the only ones who have noticed these problems. Over the last 10 years, there have been many attempts to solve them. Google took one of the first stabs in 2006 with the Google Web Toolkit, better known as GWT. GWT took the stance that all code should be built in Java server-side. The client code was then actually generated by Java code. Soon after, Ruby on Rails released RJS. It was a Ruby DSL that allowed JavaScript to be created and sent down from the server to the client. When the client got that JavaScript, it would just blindly eval it. Now, the positive effect was that you could do some neat Ajax-y kind of functionality using only Ruby code. But the problem was that there was deep criticism about security issues and bad design. In the end, the feature had to go. Popping up as one of the first JavaScript frameworks was Backbone. Now, Backbone was very good at being able to apply behaviors and manage changes of elements that had already been put on the page from server-side rendering. It was a great way to transition from a purely server-side app to a hybrid app. Unfortunately, as time went on, it suffered from not having the rich feature set that others like Angular and Ember had. the arrival of Node.js sparked developers' imagination. Now, if you were programming in JavaScript both on the server and the client, what kind of opportunities would there be to take large amounts of code and share them between both environments? Could it be done? The answer seemed to be yes, or at least yes-ish, but it was pretty hard. In order to do that, you need the same kind of conventions and libraries on both sides so that you could run the same code in both environments. This is hard to do if you don't have a framework of some kind that is built for both environments. So along those lines, mustache templates became very useful for teams who were trying to figure out how to share their templates across systems, even systems that were using different frameworks or different languages. Mustache is pretty simple, and so it was easy to implement in a number of different languages, making those mustache templates highly portable across systems. Meteor.js is notable for taking just about the exact opposite stance of GWT. Whereas GWT would actually create everything on the server and then send it down to the client, Meteor.js allows you to write browser code that then automatically implements the server implementation. By creating data definitions in the browser, the server is flexible enough to then dynamically create all of the endpoints and web sockets that you need in order to display the UI. Now, I would be remiss not to mention Angular, Ember, and React, the big three in the world of JavaScript frameworks right now. They all have deep technical excellence, wide adoption, and plans for cross-platform support across the browser, servers, and mobile platforms. My only hesitation is knowing how quickly the world of JavaScript frameworks changes. By the time that this video airs, who's going to be on top? So, here we are. We've talked a lot about how our industry got here in the first place and how the deck was stacked against front-end developers from the beginning. The early web created, inadvertently, a culture of poor code quality. We've discussed the divisions between developers and how there were very low expectations coming in for front-end developers. Finally, we discussed how client-server architecture has changed over time and add additional complexity to our applications. It's now harder than ever to maintain best practices and dry code. Now sure, there's a lot of reasons why it's hard to get front-end development right. That said, I've never been more encouraged that now is the right time. The tooling that we have is better than it's ever been before, and it keeps getting better. The projects that front-end developers are working on are getting to be more business critical, and organizations are starting to take code quality very seriously. Most importantly, I'm seeing front-end developers who want to hone their skills and own their results. I'm excited that you're on this journey with me. Now that we've laid some of this groundwork, it's time to go deeper into the solid principles and see how they apply specifically to front-end code. We're going to be doing a lot more coding. There's going to be a lot of lessons that will be directly applicable to your day-to-day work. So do not miss episode 2. And so with that, I'm going to go choke down the rest of that smoothie. I'll see you next time on Clean Code in the Browser.
Remember, you've got the power to bring beauty back. Bring beauty back. Remember, you've got the power to bring beauty back. Bring beauty back.
Why is it that projects fail? I mean, there's a lot of reasons, probably as many different failure modes as there are projects themselves. Every project is a unique combination of business concerns, technical issues. Miles, I'm getting too close. Okay, maybe I need to slow my roll a little bit.
But a rewrite, well, that gives us a chance for hope, for love, for good feelings. One more time.
Action.